Last two lectures we studied how to find fundamental units in real quadratic fields. Yeah, we did something slightly weaker than that. We found ways of finding solutions to Pell's equation x square minus dy square equals 1. And yeah, today we are going to look at biquadratic extensions. Okay, so today we will study k equal to q square root of m and square root of n, where m and n, where m and n are distinct square free integers. Okay. So, they are not equal to and not equal to 1, of course, because yeah. So, you see firstly k over q is a Galois extension. Unlike this purely cubic field that we are looking at, this is a Galois extension, and Galois group of k over q is isomorphic to z mod 2z cross z mod 2z. Right. In fact, I like to draw a diagram always of this thing. So, q square root of m square root of n, and then there should be 3 quadratic extensions inside this, right, and 2 are obvious ones. Okay. There are 3 subgroups of z mod 2 cross z mod 2 of order 2, and so what is the third one? The third one is q square root of m times n, and since m and n are distinct, m times n will not be a square, right. So, this is also degree 2. So, what we do is we put k equal to m times n divided by GCD of m n square. So, they are m and n are distinct, but they could have common factors. So, GCD could be bigger than 1. I just divide out by this. So, q square root of m n is same as q square root of k, right, is a degree 2 extension of q. All right. So, we want to understand what are all the, we find the ring of integers, of k, right. This it's yeah, and also discriminant, etc. So, we will do that in a bunch of steps, right. So, alpha belongs to OK if and only if yeah. So, this is the kind of first step, and you can norm from k to q square root of m of alpha is in O q square root of m, and trace from, yeah, maybe I have not been writing it this way, right. I have been writing it somewhat differently. Yeah. So, let me write it the way we usually write it. So, norm from k to q square root of m of alpha is also in the ring of integers, right. So, this is kind of amazing because it is saying that you can detect whether something is in the ring of integers of k by just taking norm not all the way down to q, but only down to q square root of m, okay, norm and trace. Okay, and so why is that? Well, this is not hard to prove. So this is easy, and so we go the other way around. So let's say that right. So yeah, I mean this simply means so if norm from k to q square root of m of alpha and trace from k to q square root of m alpha are algebraic integers, then alpha is and alpha is algebraic over O q square root of m, right. So, it is and so hence alpha is algebraic, right, I mean integral over z, right. So, alpha belongs to OK. So, it is a very easy observation, but it is going to be very useful for us. All right. So, that is one thing. So, we are going to do this in a bunch of steps. So, that was our step 1. Now, let us say so there are various cases now. We saw that when we looked at square root of q square root of m, the answer for ring of integers depended on what m was modulo 4. And so, you could expect a similar answer, you could expect a similar sort of shape of answer for q square root of m square root of n. But now there is this third thing k, and the answer will depend on what m, n and k are modulo 4. So, suppose m is 3 mod 4 and n and k, they are both 2 mod 4. Right. Then alpha belongs to OK implies that alpha is a plus b square root of m plus c square root of n plus d square root of k by 2 for a, b, c, d in z. Okay. And so, that is what we are going to prove first. So, why is this? Well, you can write this as a0 plus b0 square root of m plus c0 square root of n plus d0 square root of k, where a0, b0, c0 and d0, these are all in Q. And now I just simply take norm from k to q square root of m of alpha, and what is this? This is right. So, this is an automorphism that fixes square root of m, but then it takes square root of n to minus square root of n and square root of k to minus square root of k. So, I get a0 plus b0 square root of m plus c0 square root of n plus d0 square root of k into a0 plus b0 square root of m minus c0 square root of n minus d0 square root of k. And so, this is a0 plus b0 square root of m squared minus c0 plus square root of n plus d0 square root of k square, right. And when you compute this, this should be inside square root of m. So, let us see q square root of m. So, let us see if we get that a0 square plus b m times b0 square plus 2 a0 b0 square root of m minus c0 square times n. So, n c0 square plus k d0 square plus 2 times c0 d0 square root of n times k. and you see that square root of n times k should be something, some rational, some integer times square root of m, right. Okay. So, yeah, so what do we get? We get that, so that is one thing, and then the second thing is we look at trace from k to q square root of m of alpha. This is a0 plus b0 square root of m plus c0 square root of n plus d0 square root of k plus a0 plus b0 square root of m minus c0 square root of n minus d0 square root of k. So, this is 2 times a0 plus 2 times b0 square root of m, and this should be in O square root of m, which is equal to z square root of m, because m is 3 mod 4, right. So, this implies that 2a0 is in z, 2b0 is in z. So, that is one part of our, that is half of our things done, and next we know from the previous thing that yeah, a0 square plus m b0 squared minus c 0 squared n c0 squared minus k d0 squared, this thing is in z. Yeah, maybe I should, from here I should do, and similarly trace from k to q square root of n of alpha. This is 2a0 plus 2c0 square root of n. This is in z square root of n, and trace from k to q of square root of k of alpha. This is 2a0 plus 2d0 square root of k. This is also in z square root of k, and so this implies that a0, b0, c0 and d0, they are all in half, they are all at most half integers, right. Okay. So, that is fine. Next I will use this. So, next we will use this. So, next we use this. Okay. So, what do we get from this? Right. So, let me now write it as follows. So, a0 is a by 2, b0 is b by 2, c0 is c by 2 and d0 is d by 2. A, b, c and d, these are integers, right. And so, if I go back to my equation here, I get a square by 4 plus m times b square by 4 minus n times c square by 4 minus k times d square by 4. This is inside z, and so I get a square plus m b square minus n c square minus k d square is inside 4z, right. So, modulo 4, this should be 0, right. So, mod 4 yeah, and I know that this is even, as n is congruent to k is congruent to 2 mod 4, right. So, this is even, and this is, so a square plus m b square is congruent to a square plus 3 b square mod 4. In particular, this is even. So, if a and b are, if either a or b is odd, so let us say a is odd and B is even, then this is odd, and if A is odd, B is even, then again this is odd, so it can't be even. So, they both have to be even mod 4. So, hence A and B are even, which means that A0 and B0 themselves are in Z. Right, and in any case this means that so hence n c squared plus k d square is congruent to 0 mod 4, and this can happen only, so this is so this implies that c is congruent to d mod 2, right. So hence I can write, so hence 1 square root of m square root of n square root of n plus square root of k by 2, this is an integral basis of OK, right. So, this is one case that we have done now, right. Yeah. So, this is one case. Now, you can look at another case. So, another case which is m congruent to 1 mod 4 and n congruent to k congruent to 2 or 3 mod 4, right. Okay. So, so again we would so if you remember, where did we use the fact that yes, so we use the so let alpha equal to a0 plus b0 square root of m plus c0 square root of n plus d0 square root of k be in OK, and A0, B0, C0, D0 be in Q, right. And so, we can again look at, so consider trace from k to q square root of n of alpha and trace from k to q square root of k of alpha to show that A0, not B0, C0, D0, these are half integers at most, right. And there is slight difference now. If you look at trace from k to q square root of m, this is 2a0 plus 2b0 square root of m, right. This belongs to z 1 plus square root of m by 2, right. Right. So, if I write this as x plus y 1 plus square root of m by 2, then what do I get? I get x plus y by 2 plus y by 2 square root of m, right. And so anyway a0 is in half integer, that is still true, and 2b0 yeah, so okay, so right, so fine. What I have is okay, let me do it this way. So, x and y are integers here, right, and 2a0, this is an integer. So, x plus y by 2 is also an integer, which means that y by 2 is an integer, which means that 2b0, which is y by 2, is also an integer, right, which means that b0 is half integer. So, so the argument used in this case is slightly different, but nevertheless we still get that alpha is a plus b square root of m plus c square root of n plus d square root of k by 2, where a, b, c and d, these are integers. Okay. Now, next what we need to do is we look at right. Okay, so y is even here. Okay. Next we want to, so we want to conclude that a and b have same parity and c and d have same parity, and the way we kind of did this was looking at norm from k to q square root of m of alpha. So, we computed this in the previous case, and norm isn't going to change. Yeah, it's still going to be something like this. So, at least one component of it. So, let me write that down. So, it is whatever it is, which tells you that a square by 4 plus m b square by 4 minus n c square by 4 minus k d square by 4. This is in z. Yeah, I am not sure what exactly I should look at. So, let me try this, and then it will be something like this, right. So, this has to be in z now. So, which means that a square minus m b square plus n c square minus k d square is in 4z, right. And again I will do the same kind of analysis. So, say n is congruent to k is congruent to 2 mod 4, right. Then this thing will be even, hence a square minus m b square is even, but m is 1 mod 4, right. So, I should have, so hence a is congruent to b mod 2, and if a is congruent to b mod 2, then I get that a square minus m b square is congruent to 0 mod 4, which means that n c square minus k d square is congruent to 0 mod 4, which means that c is congruent to d mod 2. Okay, there is no other way that this can happen, and I can similarly take the other two cases. So, in any case, yeah, maybe let me not write it that way. So, yeah, let me say that if a is not congruent to b mod 2, then a square minus m b square is congruent to a square minus b square mod 4, which is congruent to plus or minus 1 mod 4, right. So, one of them has to be even, the other one has to be odd, and let us say that k is congruent to n is congruent to 3 mod 4, then n c square minus k d square is congruent to yeah, d square minus c square mod 4, and this thing is congruent to 0 or plus minus 1 mod 4. Right, okay. Yeah. Okay, so there is one thing that's still possible, which is that a square minus b square is congruent to 1 mod 4 and c square minus d square is minus 1 mod 4. So a is even, b is odd, and d is even, c is odd. So those kind of things can happen, which will give me 0 mod 4. So I want to rule that thing out. I want to show that a is congruent to b mod 2. Yeah, okay. So let's say a is congruent to b, no, not b, a is congruent to c is congruent to 1 mod 2, and b is congruent to d is congruent to 0 mod 2. So this way, or the other way around, those are the only two things that can happen. Then I can consider norm from k to q square root of k this time of alpha, and I'll get something like a square minus, so you see this, yeah, a square minus m b square minus c n square plus d k squared is in 4z, right. And then I'll from that I'll get that a square minus c n square is in 4z. Yeah, I just wrote the wrong exponents here. I want n c square, n c square. Yeah, and so a square minus n c squared is congruent to a square plus c square mod 4, which is congruent to 2 mod 4, right, and that is a contradiction. Okay, so this case cannot happen, and similarly a congruent to c congruent to 0 mod 2 and b congruent to d congruent to 1 mod 2 cannot happen, right. Hence, the only thing that can happen is a is congruent to b mod 2 and c is congruent to d mod 2, right. So hence, 1 plus square root of m by 2 square root of m, no, not square root of m, square root of n square root of n, oops, and square root of n plus square root of k by 2 is an integral basis of q square root of m square root of n. Okay. Yeah, so the only case that remains now that we will do next time is when m, n and k are all congruent to 1 mod 4. Right. Everything else can be obtained by rearrangement of these cases. So, next time we will do the case when m, n and k are all congruent to 1 mod 4. Thank you.